Okay, so in section 1.2, we're going to be looking at the real field and its extended system. Again, it's chapter 1 from Walter Rudin's Principles of Analysis, so maybe it's a lot of the stuff you've maybe already seen from other classes. So this should maybe just be review for some of you, and for others learning it for the first time, we'll have some interesting material. So we begin actually with a theorem rather than a definition. And just a reminder, dark blue boxes represent a theorem. So here we have a theorem that says there exists an ordered field R, which has the least upper bound property. Moreover, R contains Q as a subfield. So the rationals are a subfield in the reals. Another theorem we have is if X and Y are real numbers and X is greater than 0, then there's a positive integer n such that n times x is greater than y. And that you may know from another class. We give it a name, which is r. That's an r. Let me erase that. This is what we call the arc principle. Or if it's not the Archimedean principle, it could just be Archimedean property. And before I even prove the Archimedean property, this theorem up here, the first one, this is a really long proof. I think everyone should at least read it through once, just for this class. It's quite interesting. You can find it in Walter Rudin's Principles of Analysis. In this case, it would take me, honestly, probably about an hour to go through the proof. Which is why I'm not stating it or proving it here. But we do have to keep this theorem in mind. It is an important one, that R is an ordered field and it does have the least upper bound property. So I'm just going to erase this so we can move on. Next we have the proof for the Archimedean property. So first we're going to let A be the set of all nx, where n runs through the positive integers, right? And x is positive as well, as we see up here. Okay, if the theorem were false, then y would be an upper bound of A, right? Because this wouldn't be true if the theorem were false, so y would definitely be an upper bound of A. Okay, but A, as we saw from the theorem above, A has a least upper bound in R, right? And we're going to call that upper bound alpha. So alpha is the supremum of A. Well, since x is greater than 0, A minus x must be less than alpha, right? And alpha minus x is not an upper bound of A, because alpha is already the least upper bound. So alpha minus x is less than mx for some positive integer m. But alpha being less than m plus 1 times x is in A, right? Well, this is in A and it's greater than alpha. But wait a minute, that's impossible. Oh, before I even go through that, the way we just did that is move this to the other side. So over here, plus x, factor out an x, we have m plus 1. So this here, m plus 1 times x, is greater than alpha, and it's still in A. But that's impossible, because alpha is the supremum of A, which it is also an upper bound. It's the least upper bound, and that gives us our contradiction. Therefore, this theorem is true. Okay, and then we present another theorem. Oh, here's an illustration of the Archimedean property. So if you have B You can always find an integer n such that n times a is greater than b, right? So in this case, they're multiplying a once, twice, 3 times, 4 times, and so 4 n is equal to 4 because 4a is now greater than b. Okay, and we go now to the theorem. And before I even present it, I just want to bring up, it's cut off here, but it's the density property. And as you can imagine, between any two real numbers, there is a rational number, right? So if x and y are reals, and x is less than y, then there exists a p, which is rational, such that p is between x and y. Okay, we're going to go ahead and prove that. Well, since x is less than y, we can just rewrite it as y minus x is greater than 0. And the Archimedean property gives us what? Well, the fact that because this is greater than 0, we can multiply by some n for it to be greater than 1. Right? So we're going to go ahead and use the Archimedean property again to get positive integers m1 and m2. And the reason for it may not be immediately obvious, but you'll see why we're choosing these m1 and m2. But anyway, we apply the Archimedean property again to obtain these positive integers such that m1 is greater than nx and m2 is greater than negative nx. This is going to make some inequalities work right now. But again, the Archimedean property guarantees that these m1 and m2 exist. And therefore, so nx is greater than negative m2, right? You can do some algebra here. And less than over here, less than m1. So hence there's an integer m such that m is greater than nx and nx is greater than or equal to m minus 1. This here in parentheses might help you, but first time reading this proof, I think it confused me more than it helped me. So go ahead and read this without using that, this note here in the parentheses. But after you understand the proof, you'll see why they put this. But what we're trying to get at is that we have an integer m such that it's greater than nx and nx is greater than or equal to m minus 1, that there exists that integer m. Why? Well, because now we can combine inequalities, right? We have that nx is less than m, right? From, let me erase everything and I'll color code. M is less than nx. And then m is less than or equal to 1 plus nx. We get this from this over here, doing some algebra there. Which is less than what? Which is less than n times y. And where can we get this from? Well, we can guarantee it by doing some algebra over here. So what does this tell us? Well, we can divide everything by n, since n is greater than 0, which guarantees that the rational m over n is between x and y. So we just set p equal to this rational number, and we have that rational number between x and y. Okay, it's another pretty important theorem. It's interesting. It says for every real x greater than 0 and every integer n greater than 0, there's one and only one positive real y such that y to the n is equal to x. So what is this saying? This is pretty much saying that the number y is uniquely written as the nth root of x, or x to the 1 over n. And again, this proof is lengthy. It's not as lengthy as the first one, but this would take it would take a while. and it's not our main focus in this class. So we're just gonna do a sketch of the proof, like the reasoning behind it, right? So that first, the unique, there is one and only one positive real. The uniqueness is clear, right? And why is that? Well, if we have y1 and y2, where y2 is greater than y1, well then that implies if n is greater than 1, if n is greater than 0, that y to the n is greater than y to the n sub 2 is greater than y to the n sub 1. So it is clear that there's at most one such y. So we are going to let E be the set consisting of all positive real numbers t, such that t of n is less than x. Here we're using t instead of y. We want to show that y to the n is equal to x, right? And there's only one such y. But we're just going to use t for a bit. And we're going to let E consist of all those positive real numbers t, such that t to the n is less than x. Okay, well if t, again, this here comes from a clever mathematician, but it's just saying, hey, if t is less than 1 and it's greater than or equal to 0, well then t to the n, since n is greater than 0, is less than or equal to t, and t is less than x, right, by this equality over here, this equation. So therefore, t is an E, and and E is not empty, right? Because, well, there exists a real number t such that this is true. Now, what happens if t is greater than x and greater than 1? Well, we have that t is greater than 1 plus x. So because, again, n is positive, t to the n is greater than or equal to t, which is greater than x. So, actually, now that I'm reading this, t is not an E. This should be a not. Actually, let me write it in black so we can see that. This was confusing. If t is greater than 1 plus x, then tn is greater than or equal to t greater than x, so that t is not an E, right? Because it's greater than x. So 1 plus x, we can guarantee, well, that t is an upper bound of E, right? It's not an E, it's greater than it, so it's an upper bound of E. But why do we do this? Well, because we can guarantee now that because the real number is being filled with the least upper bound property, we get the implication that y, or I guess it implies this existence, right? It implies the existence that y exists, and it's the supremum of E. Well, y can definitely be supremum of E. Y can be greater than the supremum of E. And y can be less than the supremum of E. So what do? Well, we can show that y to the, oh, sorry, I should have wrote, no, yeah, we can show that y is y to the n less than x and y to the n greater than x both lead to a contradiction. So y to the n must equal, or in this case, x. Which is a supremum of E. I forgot the little exponents of n right now. But we can guarantee, we can show that these lead to a contradiction, and therefore y to the n must equal x. And we're going to see a little example right now with decimals. so it could make things a bit easier. And again, these proofs aren't as straightforward as other classes, but it's the beginning. It just takes some algebra working out, and then you'll see how clear these proofs are. And again, this was just a sketch of the proof. But now we can move on to a corollary, where it says if a and b are positive real numbers, and n is a positive integer, well then a times b to the 1 over n is the same thing as a to the 1 over n times b to the 1 over n. And we're taught this in high school, but don't really question why that is. So again, this chapter 1 goes through, constructing this real field and showing its properties. This proof, we just let alpha equal a to the 1 over n and beta equal to b to the 1 over n. Well, now what happens if we just multiply a times b? Well, a times b is equal to alpha to the n times beta to the n, which is equal to alpha times beta to the n, since multiplication is commutative. And because the theorem we just proved gives us uniqueness, we can conclude that a times b to the 1 over n is equal to alpha times beta, which is equal to our desired result. Okay, now we're going to be talking about decimals. We're not going to go over it because they're not really mentioned in this class. But there is what's interesting about them, something interesting. And here, I know it's a lot to read. I promise you it's easier. It's the easier part of this lesson. So we're going to let x be a positive real number. And we're going to let n not be the largest integer, less than or equal to x. So we're going to choose these here. And how are we going to choose those? Well, we're going to let nk be the largest integer, such that n naught plus n1 over 10 plus so on and so forth, all the way to nk over 10 to the k, be less than or equal to x. And we're going to let e be the set of these numbers, of all these numbers, less than or equal to x. Well, the supremum of e will actually equal x. And again, maybe you need to take a moment to read it, but I'll go over an example to make this easier. Say, for example, our x was 9.125, right? Then n naught is the integer that's here. X is equal to 9.125. Actually, I'm going to write it up here. X is equal to 9.125. So what's the integer, the largest integer that's less than or equal to x? Well, 9, right? So n sub 0 is 9. Now, n1 in this case is 1 over 10. It's still, if we add n0 plus n1, we get 9.1. And over here, n2, we chose 2, but it could have also been 1 because it would still be less than x. And then over here, n3, this is supposed to be n3. We chose 5, but it could have been 4 or 3 or 2 or 1, right? But the reason we chose exactly 9 and 1 and 2 and 5 is because we're getting the supremum of all these numbers e. Right, so in this case, n sub 0 is equal to 9, n sub 1 is equal to 0.1 now, like this new term, this new number. 1 over 10, 2 over 100 is 0.02. This new number is 0.001, 0.005. And if we add those numbers, they're going to equal x. So that's why it's saying the supremum of all these numbers that we choose added together is equal to x. But again, we're not going to be using decimals much in this. So next we're going to look at the extended real number system. And then we'll be done. This extended real number system is, we'll be using it later on, but there's not much to it for now. And it's the definition for it is the extended real number system consists of a real field R and two symbols, infinity, positive infinity, and negative infinity. And we're going to preserve the order in R in the real numbers. And we're going to define negative infinity to be less than x for every real number, and positive infinity to be greater than x for every real number. So we have this number line here, positive infinity is on the right side, negative infinity, and we have the real line. Right, so if x is real, then if we add positive infinity to it, it just equals positive infinity. This just goes with what your intuition tells you. X minus infinity is negative infinity. And maybe you've seen in calculus class that, actually I'm sure you've seen it in calculus class, x divided by infinity, by positive infinity or negative infinity will be equal to 0. Just as we take limits in calculus. If x is greater than 0, or in other words, if x is positive, then x times positive infinity will just equal positive infinity. And x times negative infinity is just negative infinity. What happens if x is negative? Well, then x times infinity is negative infinity, and x times negative infinity is positive infinity. Again, here it was like negative times a negative, positive. Over here, negative times a positive is a negative. And this real line above, I just have it because, well, if we have any sets here of real numbers e, obviously negative infinity and positive infinity are lower and upper bounds respectively. But if we're to have a set of real numbers that, well, isn't bounded, say e is from just bounded below, well, then in that case we would say with the extended number real number system that the suprema would be equal to positive infinity. Same reasoning applies if e were bounded above but not below, and if it's not bounded above nor below, well, then our infimum is negative infinity and our supremum is positive infinity.